Okay, so Francisco, you can start right away.
Okay, thank you. So I'm Francisco, first year PhD student, supervised by Tanya and Alda. And in this journal club, the main objective is to introduce some ideas related to the work that has been done with causality in machine learning, with the help of this paper chosen for discussion, which is the generalization in anti-causal learning. So this is the article. Okay, the main problem we are addressing today is the generalization problem, and there are several examples of this limitation in many machine or deep learning tasks. These images, these three images illustrate this problem, where detecting a cow in the beach would be a very difficult task for many typical detection models. So these two terms, weak and strong generalization, refers to this ability to generalize over only identically distributed or out of distribution test sets. The idea here is to explore this problem and understand why it happens, and see possible solutions through a causal perspective. Okay. Let's first clarify these concepts that are introduced in the beginning of the article, which is the causal and anti-causal models. We have a causal model when the variable we are observing is the cause, in this case is x, and in the anti-causal situation, the effect is the variable that we are observing. In the first, given the cause, we are predicting the effect, and in the second is the opposite. We try to predict the causes. Giving some real world examples for the causal scenario, we have this plot with the altitude and temperature, and in this case, x is causing y. And for the anti-causal example, the identification of a digit from the MNIST data set. Here we are observing the images, we're trying to predict the cause, and so the image 3 is the effect. And as you can see, most of the typical machine learning image-based tasks we are used to do daily are anti-causal, and we basically try to infer some information about the images we observe. Okay, moving on. This independence between cause and mechanism principle is more generally is a principle that says that in a causal model, the causal mechanisms, each one from each cause to each effect, are independent between each other. And here we are looking to a more simplified situation, which is only looking for two variables. Looking for the same examples before. In this two variable situation, the principle says that the distribution of the cause and the causal mechanism should be independent. But what are the actual implications, and why is this important to the generalization problem? If you look at this formulation of the principle, what it says is that seeing a change in the distribution of the effect y in the causal model, this change must have been caused by changes in x, by the cause. But there is no reason to believe that the causal mechanism, the mechanism that computes the y from the x, has changed. So in a causal model, there's this independence between the causal mechanism and the distributions of the cause or the effect. In the anti-causal model, the prediction mechanism no longer matches the causal mechanism, so we can say that there is any independencies here. The Py given x is not independent of the distribution of the effect, nor even the cause, and this is the reason why semi-supervised usually helps, mainly when we have labeled data sets that are small. If we give more examples of the x distribution, even if it could be be unlabeled, but it actually gives more information on our prediction mechanism in the anti-causal direction, because there is no independence between the mechanisms. On the other hand, in the causal scenario, given this independence, more X variables will only tell us more about X itself, not about anything else. So semi-supervised learning is not expected to cause any improve in our prediction ability in causal tasks. Looking to this in a more practical way with examples, these are two anti-causal examples. In the left, in these digit classifications, we can view all the process that took the writer to actually write this exact digit 3 as the digit label, and we can idealize the cause as being the label. It's a more high-level concept of the cause. And in the right, in more complex causal structures, often we don't need to infer the cause this set of causes in full detail, but here we would need a very more complex set of causes, larger, with more variables, and each one presenting each specific effects on the image. And one of these causes would be our level of interest, which, for example, can be the presence of a malignant tumor, cancer. Okay, with these examples, we saw that there is some flexibility, not only on how we idealize what could be the cause, but also in the set of causes that we are considering for a problem. We can, for example, modify our data set and include some modifications with some typical data augmentation techniques, and we can include these modification variables in our causal set because it has an actual effect on the image we are observing. We have, in this example, we have a new cause M that it is supposed to encode only the modification of the image, and we can explore the development of a model that is able to recognize these 3 independently of how rotated it is, because it's still a 3, and this example comes from this article that I leave below, and you can read more about it if you're interested. Okay, if we can think about this flexibility, it can open many doors for some domain adaptation and knowledge transfer tasks. Because it gives us the possibility of dynamically introduce new classes, as we saw before, and only learn the mechanism that infers this specific novel class. It's like a modular design that enables to learn the path for each cause, and since these mechanisms are independent, we saw that from the ICM principle, introducing new mechanisms should not change the old ones, and we can introduce new variables and learn to infer these new cause without changing the old ones. Okay, moving on to this next section. Here we'll see some examples that can help to understand why it is so difficult to make predictions in the anti-causal scenario. According to this book by Vladimir Vatnik in 1998, there's a clear difference between imitation and identification. From one side, imitation is achieved by this empirical risk minimization, which is anything more than just the training process of any typical machine learning algorithm, where several hypotheses are tested, and the one that minimizes a certain loss function is the one that we choose in the end. On the other hand, identification refers to a deeper knowledge that only can be achieved if we invert the forward mechanism, and the forward mechanism will be the causal mechanism. And we might know this causal mechanism or not, and this inversion is sometimes theoretically impossible or very difficult to solve. And here I'll give you, there are several examples of this hardness of this inversion. We can see that in the article. I will introduce one more here in the presentation. This next example is about causal discovery, and it relates with this minimum description length, and this is related to both model and data compression. And the idea is that compressing a model is basically extracting the redundancy from it. And when in this article, when they analyze the causal and anti-causal directions, they found that the anti-causal presented higher MDL scores, which means that compressing an anti-causal model resulted in a longer description of this model. And so if the causal model provided a shorter description, which means less redundancy, it is expected that its generalization ability is higher than in the anti-causal direction. Now, just to remind the main problem we are discussing here, and bringing the first slide again, we are trying to understand how to achieve a strong generalization in anti-causal tasks, a generalization that is able to correctly predict in arrow distribution scenarios. And we are presented with a possible solution, and this is a figure from the article, and given some observed defects, which can be an image, this variable y, and assuming that we have access to the causal model, we can infer a certain set of causes and validate them by running the causal model. If the output matches the effect we observed before, the inferred causes are true. And if it doesn't match, we have to iterate over the anti-causal model and try to find a different set of causes and validate, and so on until we find valid causes. And looking to this, there are some clear barriers in this possible solution. And having access to the causal model is a strong assumption. Perhaps it can be easy in very simple structures, very simple tasks, but not in more complex situations. And it ends up being reduced to an iterative search problem. It's in line with what we saw before. Sometimes an exhaustive search is the only solution to find the inversion of the forward mechanism. But here the main problem ends up being to find an optimized way to do all this search. Okay, now we look into some implications and possible ways to implement this search. First, in generic deep learning applications, here the problem is digit detection. It's many use in research in this topic, and here we are trying to not only detect but reconstruct an image without knowing how many digits the image will have. In a quick description of the model, looking to an image, three types of these Z variables, the red, the green, and the blue, are inferred. The Z pres is an interrupter variable that should be inferred to 1 if there's one more digit to process. The Z where encodes information of the location of the digit, and Z what represents the latent variables that are related to the digit itself. And the interesting part here is that this RNN framework allowed to look at one digit at a time until Z pres was inferred to 0, like a while loop that runs until there is no more digits in the image to look. And it is actually shown in test time that the model was able to detect more digits than what it was trained for. For example, a model like this was able to detect and reconstruct an image with 3 digits, when it was only trained with image with 1 or 2 digits. And given this flexibility to look at 1 digit at a time and to stop where is some condition, it is argued that this flexibility that these RNN brought might make possible to implement this cycle, where in practice we don't know which will be the final causes that are actually the valid ones, and we don't know also how many causes we are supposed to extract from an image. In the adversarial examples, something that we all have seen showing how susceptible certain classification models are to these changes. Basically, there is a large reaction when the input is slightly modified. But looking to this through a causal perspective, an attack in our observations should not affect our generalization power. Why? Even if we look to attack observations and we try to learn to infer these adversarial causes, because they in principle should be validated by the causal model, these causes will be connected to their specific effects on the image and not being our cause of interest. That the adversarial cause is not the one we are trying to predict most of the times. The classification process should be invariant to these adversarial causes. We are trying to predict one cause, normally one cause of interest, and not the adversarial ones. So in this article, which is related to this problem, is about selective classification, which is basically only classify what we have a certain level of confidence, not we, but the model itself, right? And the paper is introduced with this sentence, which is, what I cannot create, I do not understand. And very quickly, what they did was, with a basic CNN, this plot on the left shows the curve that relates the percentage of the data set, which is this coverage variable, that was classified, and this percentage is based on the confidence that was established in the first place as a minimum. For example, we can say that we only predict the class C for an image if its prediction is above 80% or 90%. So changing this level will change the amount of examples that we are classifying in the end. So we see that for a 90%, something like that, of coverage, the error was 0, and then it decreased exponentially when this confidence threshold increased. So this basically says that it might be reasonable to think that the higher the prediction confidence, the more we can trust on that. However, this was done with the MNIST data set, but when they introduce a new data set with images, this omniglot data set with images that the classifier had never seen, we could guess that the same plot will be something like this. So it is with these new data sets representing about 76% of the final data set to be classified, we could imagine that the MNIST examples would be classified with high confidence. And then when trying to predict these omniglot examples, the model shouldn't have such confidence, and we should be able to draw this red line, the dashed one, that separates these two data sets based on the confidence of its predictions. However, this is what happened. If we note that the Y scale has changed, it's around 100 times bigger. If we look at the blue line of the CNN to make a direct comparison, we can see that clearly examples from the omniglot dataset were classified with high confidence, which doesn't make sense at all, of course. And based on this initial claim that we only understand what we can create. Two generative models, GAN1 and the variation autoencoder, were trained with the MNIST data. And in the end, for each example supposed to be classified, the generative model tried to create the same image, and only images with reconstruction errors below certain levels were actually classified. And we can see that mostly for the GAN approach, a scenario identical to the one we imagined in the first place was actually achieved. Okay, for the encoder decoder section, we see that from a causal perspective, there is this possibility of taking more of this architecture than just building a neural network that is able to reconstruct what it sees. Because when we only care about the reconstruction error, when building a basic convolutional autoencoder, this is what the latent space actually looks like. An input image is encoded to one point by the encoder, and only from that point it can be retrieved, which is actually very limited in its utility. But what if we see the encoder as the anti-causal direction, the anti-causal model, which will map the effects, our observations, into causes, and the decoder as the causal model? And for this, we need to force the encoder to extract valid causes, and there is a lot of work on this with the implementation of the variation autoencoder and several improves on this architecture and the learning process. And this is an example, and it is possible to see that improving the latent space efficiency, because now we are not just concerned about the reconstruction error. There is a decrease in the output, in the quality of the output. But if we compare this latent space navigation with the previous one, here there's much more organization and efficiency. And we can move to the class of the digit 3 to the 8 very smoothly and generate new examples that actually mean something. And this term, disentangling, has seen a lot of research, but essentially what is necessary is the ability to extract and separate, which means the disentangle basically, the causes that have a clear effect and that are independent. To implement this intended search for valid causes, some adaptations would be required in order to have an iterative encoder to implement this search for new causes, and a fixed decoder. Sorry, and a fixed decoder for the validation of the causes. Okay, in contrast with some of the examples we saw before, Bayesian inference has this characteristic of using our knowledge of our prior beliefs about the data, despite what we are observing. In this example, note this change, this time X is causing Y. This needs to be clear. And by the Bayes theorem, this is how the distribution of the anti-causal direction is actually computed. However, explaining any problem with this level of simplicity is often not possible. In computing these distributions can become really complicated, and the mathematical explanation is not covered here, but you can find several papers on this. And there are some sampling and optimization-based alternatives for this computation. The most common approximation alternative is variational inference. And with variational inference, it allows to approximate our complex anti-causal distribution to more simple ones. In a nutshell, each mechanism is learned by a neural network, and in the typical case, the latent space is forced to approximate a normal distribution. And this actually explains why it is possible to navigate through the latent space and find meaningful new images, as we see in the variation autoencoder slides before. And finally, I'll leave you with some connections with other concepts, other fields, which are given in the article. And first, highlighting the similarities between this proposed solution for the causal search and mainly the first step of the scientific method. And then when we are guessing an hypothesis, we can view this as basically as an anti-causal way of thinking, because we are trying to find some explanations for things we are observing. And also we see connections with the two modes of reasoning that are presented in the book, Thinking Fast and Slow. The system one, which is associative and domain specific, the one we can expect the weak generalization power. And we can match this system with the anti-causal model that we are referring in our loop. And system two, which is the rational one, with strong generalization abilities that we can match with the causal model. And this is only a possible solution for this problem. But I think the main idea that I would like to leave today is that it's crucial to take the most out of our knowledge about the world, to improve machine learning in general, and to eventually see truly intelligent AI. To conclude, just a quick recap of what we saw today. We saw the key differences in causal and anti-causal learning. A major difference is the generalization power, and we saw why the causal direction presents a stronger generalization ability. And with an idealized solution for all these, we saw examples of what it takes to look at common machine learning or deep learning models from a causal perspective. And that's it. Thank you.